Okay, I understand what you're saying about the guy who spun the foam things in the water. That's the spinning rotations in the same direction would pull each other together, and opposite directions would push. And you've got the medium of the water being the medium of the ether. But I don't think in the water, for one thing, if he put another piece of foam that was spinning slower, because is this metal ball, it's not magnetized, does it have much spin to it? Well, not as much as the magnet. So if he was to put something in the water that wasn't spinning the same speed or as much velocity, would it pull to it like that? That's why I'm saying here, the inflow is faster than the rotation because this doesn't rotate sitting there. I know the magnet's rotating, but I think the in-pull Fibonacci moving towards each other is faster than the rotation or more powerful. And the ether it's rotating all along the magnet. The ether is spun up on both sides and all around it. It's just right in the middle. The actual magnet itself does not have that speed here that it does out here. It's the speed out here in the ether that keeps both of them spinning above the equatorial plane. Each end meshing together like a slip gear up here is why your spin's there. And even against the CRT TV, it'll pull it higher in the middle because they're both meeting there and out farther as far as that rotation. Here, the pull is farther because it's pulling in, straight in. That's why you don't have it. That's the other reason why, if you see, the magnet won't stay in the middle. There's just gravity there. It'll stay there. But then it flings to an end. And it'll stay there. You move it enough, it flings. And just depending on which way's got, the table's leaning or what have you. It'll go that way. But that's why it pulls to the ends. It's coming in. I'm going to prove that more to you. I want to get through this real quick. This is just for you. So we know it's coming into the ends because it pulls those in there. And it works through any material I put between these because it'll go right through a non-magnetic material and still pull this magnetic ball to it. It's just that has the properties to not care which way it's spinning, but yet it'll line up its electron functions with the Fibonacci. It lines up with the lateral acceleration, but there's not enough spin to spin it. Not per se. Okay, that's that point I wanted to try and make, is if he spun it in the water with, that makes sense of what he did. But what I'm showing you with this, I'm going to show you in a minute more, is with the Hall sensor, there's a reason we know it's rotating over the top towards us. The south is rotating that way, the north is rotating that way. There's no way this could discern between that light and that light if it's just rotation, because they're both putting the same rotation towards this sensor. They're both rotating over the top, down into the sensor. But yet it knows that that's the south and that's the north. For something is causing that current in there to bend one way than the other, even though the rotation is applied the same. That's what I got with this. If I reverse the rotation, it still knows. See? And it don't matter which way I reverse the rotation on the south, it still knows. And it doesn't matter which way I reverse the rotation on the north, it still knows. So it's not just the rotation, or this would not be able to discern between these two. There has to be that corkscrew. There has to be a lateral motion along with it. I'm going to show you that more in a minute with the electric current again. I've got a better way to show it this time. But again, the negative and positive on this is the same thing as the red and green on that. The negative is a red light, the positive is a green light, but when you get right to the middle, there is nothing. Goes to zero. If I get it on there just right. Right there, zero. Nope, it's positive zero there, it'll be negative zero there. Right in the middle, it's zero, but it discerns positive and negative from that 0 point. They're Fibonacciing in, they're rotating, and they're moving towards each other, but right in the middle, it just slows down in the magnet. Like I said, the reason you've got field outside the magnet at the equatorial plane is because of the bulb out here rotating, the bulb out here rotating. They're keeping each other going around the magnet. But that's not the only thing going on. It's not just a rotation. It's got that draw in from both sides. Now I'm going to show you that more with the electric current again, with a much better view and an explanation with some arrows and stuff on the magnet as the arc bends and twists, and I can show you exactly, and we'll do that. Okay, I've got my neon sign transformer set up for my arc. Okay, I'm going to zoom in a little more probably on this so you can see better, probably. Here's the magnet rotating. You see that? South rotating to the right, clockwise, so is the north. But I say they're coming towards each other, like that. Now I'm going to show you now why that practically has to be. Why this shows and this shows. That's what's going on. Okay, I'm going to zoom in and show you a closer view of it, and get it going, and get my camera in as close as I can so you can see it without the electric current. Will really messes my camera up if I get too close. When I zoom, it loses pixels, so I don't know why. So I'll do that. Okay, the current's running. It's trying to burn up my tape. So we know the south. I'm going to stay on the south now. Now watch what this does when I lean it this way. If you notice, if I can get it in there, it's trying to go down with the rotation, but it's trying to pull it back to the equator. If I can get it right. So it's trying to pull it back to the equator as it tries to rotate down. You see that right there? It's trying to pull it back to the equator as it rotates it down. It's doing this. You can see that. It's trying to bring it back right here. The squirrel comes back and then over to the ground. It's a twist, but it's like it's trying to curlicue it. You see that? It's trying to curlicue it back to your left. It's pulling it back to your left towards the equatorial plane. The input is doing it. The Fibonacci, the rotation's twisting it, the Fibonacci's bringing it back. Now, the other way, it just puts a twist in it, and it still kind of pulls it towards the equator, the twist. If you see that, it's more of just a twist. There it is, just more of a twist. See, just a twist. It doesn't have that backlash like that. See how it's pulling it back to your left? This doesn't bring it to your left. It's pulling it to the equator, see it? It's pulling it to the right. It's trying to rotate up, but it's going that way. Do you see that? And that one's more like, let me shut the power off. When it's this way, it's doing that to it. It's just putting kind of a kinky twist in it. See that kinky twist? That's what it does. It's trying to go with the rotation, but it's trying to keep going that way, and the equator is pulling it that way, but it's also rotating this way. So that's pulling it in that little twist. But the difference is, on this side, it does that back pull. If you see that back pull, it wants to do that to it. It's trying to put a curlicue in it like that. If you look at it from that angle, it's a curlicue. If you look at it from this angle, it's a twist. You see? Curlicue, twist. We're looking at the twist side. If you looked at it from the angle down here, that is what you would see. Why would it do that if it's just a rotation? See what I mean? The current's going that way. The magnet's going opposite towards the equator, but it's rotating towards it. And it's putting a curlicue in it. This way, if you look, there is no curlicue. It's just a twist. It's just a twist because it's going with the rotation, but it's going with the Fibonacci towards the North Pole, so it just twists it. Okay? Now I can use these same wires on the north, but they'll be reversed, so it'll put my red side on that side. But anyway, we'll do the north now. Okay, now I've got the north over there. You see it's feeding in this way, but it's rotating over the top towards us. It's trying to back feed it. See that back feed? I lost my arc. It's trying to curlicue it again. It's trying to curlicue it. You can see it. It's doing it back to the left. It's coming towards me and towards us. Towards me, towards the left, but straight out towards us. This way, it just twists it. See the twist? It's just a twist. I guess you can see it. Just a twist in it. It's not coming back to me, back to the left. It's just twisting. This way, it's going to come back to the left. It's going with that Fibonacci coming to your left. If the pole's with the current, like this, it just twists it. If the pole's against the current, it tries to do the loop-de-loop. Either side. On this side of the current, it does it that way. And it's just reverse over here, you see? It's still going to do the twisty twist when the current's going against the direction the magnet's trying to pull in, the Fibonacci. The rotation will go down, but it's going to try and curlicue it backwards. You know, if you put the pole away, instead of curlicuing this way, hang on, I need 5 more hands. The south curlicued it like that. The north is going to curlicue it the opposite. Like, well, I can't see, I ain't got it bent right for the north. Like that. They're opposite, but they look the same. I hope you see that. It's always, I mean, if you got the pole side towards the incoming, well, the current's going that way, it kind of goes with the rotation and just puts a curl in it, a twist, a roll, if you will, like that. It just rolls it a little bit. But when you put that pole away from the incoming, like this, you know, I'm not on the south, I'm on the north, it puts that curlicue in it. It tries to backtrack with the Fibonacci going to the equator. I don't know if you understand that and can see it or believe it or not, but that's what's going on. Okay, I'm going to use the round one again. If you look, the rotation is going with the current, right? With the current. It's going to pull it towards the equator. It pulls it up. You see that? It's not the rotation doing that, it's the Fibonacci input. Look how much it's pulling it up. And it's rotating with the current. It's taking it to the equator. If it was just a rotation, it should just swirl right across. It should go right across in a swirl. But it's going up towards the equator. You see that, okay? That's the south. Now the north. It's going to be rotating the other way, so I'm going to come from the bottom. It's rotating that way, so I got to come from the bottom. But it's still going to pull it towards the equator. You see how it pulls it to the equator? Even though the rotation's with the current, it pulls it to the equator. Either way, it's that feed in. It's trying to rotate with it, but that feed in is stronger. And it pulls it to the equator. That way on the north, because remember, I'm rotating this way with the current, but it still wants to go down into the equator. I hope you see that. The south brought it up with the rotation with the current, it goes towards the equator. And if I go against the current, of course, it tries to put a loop-de-loop in it, because it's rotating backwards. I hope you see that. It's got to be the 2 motions of the corkscrew. That's why a Hall sensor can pick it up that quick. That loop-de-loop is meeting right in the middle, but that just shifts right in the middle of this sphere. That's where the Gauss meter will go to 0 if you get right in the middle. This don't. This has always got a little bit of pull one way or the other. See how quickly that moves? There's got to be the double corkscrew motion, or this wouldn't do that, and this wouldn't pull towards the middle. Even though I'm rotating in the same direction, it's pulling it down into the center of the magnet, to the equator. I'm going to zoom in and hopefully it'll pick up. Get the zoom. All right, fire it up. I want you to watch the current always goes up towards the equatorial plane. Even down here, it's pulling it up. It pulls it towards the equatorial plane. That Fibonacci's pulling it up. I mean, if I go on the other side, it pushes it, but it pushes it down, if you see. It's not going to the tip of the magnet, not going to the pole, it's going to the equatorial plane. The rotation's more fast out here, but it's going in, corkscrewing, pulls it towards the equatorial plane. Let me do the south a couple times. If you see that, it's pulling it up. Let me do the north. And I have to go underneath to get the rotation with the current. So I have to go underneath. And it'll pull it down. See, it pulls it down. You don't go to the center. Yeah. The corkscrew, the rotation, and the infeed pull it to the equatorial more. See, don't pull it to the center. It pulls it to the equatorial plane, if you can see it. Pulls it down, south pulls it up. And when I get the center right over it, spinning so fast it blows the current in two. But it pulls it down. It pulls it toward the equatorial plane. The north does and the south does. See that? So that's what I wanted to show you.